Now we're going to look at several types of chemical reactions. We're going to learn to identify the reaction and predict its products, and even determine if there's going to be a reaction or not. This is obviously a very limited list of the possible types of chemical reactions. The possible types of chemical reactions is a very large list of chemical reactions. First one we're going to look at is a precipitation reaction. This is a type of double replacement reaction where we are mixing together two aqueous ionic solutions. So in each solution we're going to have a dissolved ionic compound, which means that we're going to have a mixture of cations and anions, creating a electrically neutral solution. So if we have two of these solutions, we mix them together, we're going to get a solution containing two different types of cations and two different types of anions. Where is the reaction? The reaction is if something removes ions from solution. So there are two possible products, two possible new combinations available when we mix these solutions together. So if one of those new combinations is removed from solution through the process of precipitation, then a reaction occurs. Precipitation occurs when the solubility of a new combination is low enough that we exceed the solubility and we precipitate out the solid. As we precipitate out the solid, it's going to form very small, fine particles. And so we won't form chunks of solution. We'll end up with a milky, cloudy solution, not with chunks on the bottom of the beaker. So to do the double replacement reaction, we're going to take the cation from the first compound, combine it with the anion of the second compound to form one of our possible products. The cation from the second compound, combine with the anion of the first compound to form a second possible product. So one of these has to be insoluble to create a reaction. And the insoluble one is going to be listed with an S for solid. Well, we're going to learn how to predict these reactions using solubility rules. On this chart here, on this table here, there's a line in the middle. Everything above the line is generally soluble. Everything below the line is generally insoluble. And you'll see that this is a list of ions. So we're not listing the whole compound, we're listing the ion and a rule associated with the ion. So if compounds contain the ion, then they follow the rule. And we start off with rules on top that have no exceptions to them. And then as you go down, we're going to have some exceptions. The first rule is alkali metal ions. So compounds containing alkali metal ions like lithium, sodium, potassium are soluble. Also, compounds that contain the ammonium ion are soluble. We're not listing any exceptions for these. We're not expecting any exceptions for these. But these are the only cations on this table for the rules. So later on, when we were dealing with the generally insoluble, these will be the exceptions to those rules, because this rule is a primary rule. Okay, moving on, we have the nitrate ion. So compounds containing nitrate are going to be soluble. Then acetate, compounds containing acetate are going to be soluble. Then perchlorate, compounds containing perchlorate are soluble. So we're not listing any exceptions for these. So these are just soluble compounds. So if you see a iron acetate, we're going to say it's soluble. If we see a calcium perchlorate, we're going to say it's soluble. Now the next one, we're going to start to get some exceptions. So halide ions, chlorine, bromine, iodide, are generally soluble. Now we're going to have a couple exceptions. Silver halide, silver chloride, silver bromide, silver iodide are insoluble. Mercury 1 halide ions are going to be insoluble. So mercury 1 is at a little dimer ion, so Hg2 with a 2 plus charge. So there's 2 atoms, total charge of 2 plus. That means each atom has a plus 1 charge. That's why it's called mercury 1 ion. And then lead 2 halide compounds are going to be insoluble. Next rule, sulfate. Compounds containing sulfate are generally soluble. Now there are more exceptions here. So barium sulfate, mercury 1 sulfate, lead 2 sulfate are insoluble. And then strontium sulfate and calcium sulfate are marginally soluble, slightly soluble. So an example would be the calcium sulfate. Calcium sulfate occurs in nature as the mineral, the rock, gypsum. We use that mineral to make drywall for our houses. And if we spill water on our walls don't immediately dissolve away. But out in nature, the gypsum, calcium sulfate, is one of the most soluble rocks that we have out in nature. So it's more readily found in desert environments. In wet climates, it tends to dissolve away on a relatively rapid scale, relatively rapid for geological processes, or long compared to laboratory processes. Below the line now are the generally insoluble ones. So compounds containing hydroxide are generally insoluble. Now our first rule of the alkali metals and ammonium ion is our primary exception here. So alkali metal hydroxides are going to be soluble. Ammonium hydroxide is soluble. We know that one is. We buy that in the supermarket as a cleaning agent. And then we got calcium hydroxide, strontium hydroxide, and barium hydroxide are slightly soluble. Hydroxide is one of the common ways that we use to treat up industrial wastewater. Wastewater that contains heavy metals. We put in sodium hydroxide, which is soluble, and then we'll precipitate out iron hydroxide, chromium hydroxide, and other metal hydroxides. Compounds that contain carbonate are generally insoluble, except for the alkali metal carbonates or ammonium carbonate. So calcium carbonate, which is a rock in nature called limestone, is considered to be a soluble rock, but the calcium carbonate is not soluble by itself. Acid rain will dissolve the calcium carbonate by converting it into calcium bicarbonate, which is then soluble. But the calcium carbonate itself is not soluble. Compounds containing phosphate are generally insoluble. And again, the alkali metal phosphates, sodium phosphate, ammonium phosphate, are soluble. And calcium phosphate is also found as a rock in nature, as an insoluble rock in nature. It's also a part of our bone structure. So being insoluble allows us to have bones without them dissolving away. Compounds containing sulfide ion are generally insoluble. And again, the alkali metal sulfides, the ammonium sulfide, are soluble. Compounds containing chromate ion are generally insoluble. And the alkali metal chromates and the ammonium chromate are also soluble. Now, the solubility rules is what I'm expecting us to know. This chart can give a little bit more detail. A chart like this can give a little bit more detail than the rules can give. But we're not going to have to memorize this chart. This chart is just available for use if you need it. So what we do when we see two aqueous ionic compounds being mixed together, we're going to identify the two new combinations, two new products that can be formed. We do that by the double displacement method. We take the sodium from sodium bromide, combine it with the acetate from silver acetate to give us sodium acetate. Take silver from silver acetate, combine it with the bromide from sodium bromide to give us silver bromide. Once we identify the two new products, we use solubility rules to tell us whether soluble or insoluble. So sodium compounds are soluble. So that's all that we need on this one. Although if we want, we look at acetate. Acetate compounds are soluble. So this is doubly soluble. Bromide compounds are generally soluble, except for silver. So silver bromide is insoluble, so that gets us S for solid, so we have a reaction. So there has to be a solid produced, an insoluble solid produced, for a reaction to occur. If both products are soluble, or aqueous, there is no reaction. So on this second one here, sodium chloride with ammonium nitrate, the two new products would be sodium with nitrate, sodium nitrate, ammonium with chloride, ammonium chloride. Well, sodium compounds are soluble, nitrate compounds are soluble, ammonium compounds are soluble, and most chloride compounds are soluble. So we have two soluble products, so there's no reaction going on. Generally, we're only going to find one insoluble product, but it is possible. I had to search long and hard for this example. It is possible to get two insoluble products. They are not common. The next reaction is going to be an acid-base neutralization reaction. This is another type of a double displacement reaction where ions are removed by producing a neutral water molecule. But first, let's go over the definition of acid and base. We're going to do the Arrhenius definition of acid and base, which is the original definition for acids and bases. There are two additional definitions that have expanded the definition, but we'll come back to those at some later time. So an Arrhenius acid is a substance that ionizes in water to produce hydrogen ions. Hydrogen ions are H+. Hydrogen atom is a proton with an electron. So H+ is just a proton, and we'll be referring to the hydrogen ion as a proton or protic in a little bit also. Although we never find the hydrogen ion by itself in water. We always find it attached to 1, 2, or 3 water molecules. So we show it being attached to one water molecule, which gives us H3O+, which we call the hydronium ion. And either form is an acceptable form. They mean the same thing when we're in water. Examples of acids, HCl, HF, H2SO4, H3PO4. And you'll see that we're all these compounds starting with hydrogen as the first element. These are our inorganic acids. Organic acids can be written in a couple different ways. So they're not as obvious as the inorganic acids. So on this one compound, I'm showing two different ways, HC2H3O2. Well, we should recognize C2H3O2 as being the acetate ion. So this is our acidic hydrogen making this acetic acid. The other way that we write it, CH3COOH, is COOH, CO2H, is carboxylic acid. So this is another way of writing it to identify the carboxylic acid group within an organic acid. Also, we see that in both cases, one hydrogen is separate from the other hydrogens. That one hydrogen is the acidic hydrogens, and the other hydrogens will not ionize in solution. Now, our Arrhenius bases are substances that ionize in water to produce hydroxide ions. So most of these are going to be metal hydroxides. Sodium hydroxide, calcium hydroxide, potassium hydroxide, magnesium hydroxide. We do have a class of compounds based on nitrogen. Ammonia is the simplest example, NH3. Amines are replacing hydrogens on ammonia with hydrocarbon groups. But for both these compounds in water, the nitrogen can take a H+ from water to form NH4 for ammonia, but it leaves hydroxide in water. So the hydroxide comes by reaction of the base here with water.